Okay, guys, so this is chapter ATA 51 to 57, covering the structures, and we're also going to look at towing and jacking as well. So this is just a very short summary video of the chapter. So as always, you need to look in the notes that accompany this to make sure you've got enough info to get through the exam. But I've produced this video just to cover the main key salient points. Okay, so we'll just crack on. The 737 then is divided into 8 major zones, and they're all identified in the AMM, etc., to help you identify the aircraft components and parts. And these are the major zones and subzones. So first of all, we have the fuselage, so that's from front to back and away from the floor line. Then we have the wings. The wing area covers the wings from the inboard all the way to the outboard, and then from the front, the leading edge to the trailing edge. Then we have zones for the horizontal stab and elevator, going inboard to outboard, and then front to back. And then we have the vertical fin and rudder, so from the leading edge to the trailing edge of the vertical stab, including the rudder. When you look in the aircraft maintenance documentation, quite often you'll find zones identified with a number, and this is fairly standard. They're using standard ATA system of zonal identification and numbering. So for zonal identification, we have a 3-digit number which identifies the major zones, the subzones, and zones as follows. So the major zone is the first digit of the 3-digit number, and it ranges from 1 to 8, followed by 2 zeros. The subzone, the first digit in the subzone represents the major zone. The second digit is a number from 1 to 6, or 9, and the third digit is a 0. And for the zonal areas, the first 2 digits represent the subzone and zone, and the third digit shows a component or group of components that are inside that subzone. If we look at the picture, you'll see, if we look at the major zones, which are, if you remember, is the first digit of the 3-digit number, numbered 1 through to 8. So zone 100 is the lower fuselage, zone 200 is the upper fuselage, zone 300 is the empennage and body station, zone 400 is the power plants and nacelles, zone 500 is the wing, left wing, zone 600 is the right wing, 700 is the landing gear and landing gear doors, and 800 is the passenger and cargo compartment doors. So if you see a zonal identification number of, say, 126, the first number tells you that it's going to be in the lower half of the fuselage somewhere, and then the 2 and the 6 are the subzones within that particular major zone. For exam purposes, you need to have an understanding of these major zones, but there shouldn't be anything new to you because it's all following ATA standards. This slide just kind of highlights these major zones. So 100 is the lower fuselage, 200 upper fuselage, 300 is the empennage, 400 power plants, 500 left wing, 600 right wing, 700 is the landing gear and landing gear doors, and 800 is all other access doors. The main structural components of the aircraft are traditional aluminium alloy riveted, aluminium alloy skin riveted to aluminium ribs and frames and stringers, etc. But where possible, we do use composite parts where there's no particular stress involved and for aerodynamic fairing purposes. The main advantages of using composite materials is that they're corrosion resistance, they have increased fatigue life, and they're very lightweight in construction. And they're also pretty strong as well. Aircraft, there are 3 main jacking points with 4 auxiliary jacking points. The main jacking points are the wing jacking points A and B, which we can see in that picture there, just sort of inboard of in line with on the fuselage right at the inboard of the wing, and the aft jacking point, the aft body jacking point. So the aircraft's lifted at those 3 points. The 4 auxiliary points identified as D, E, and F. So we've got the forward jacking point D, 3 landing gear points identified as E and F. Obviously for the F, there's 2 of them for the main landing gear. And we can use those to jack up the wheel or the axle if you're doing wheel changes and things like that. The aircraft can be lifted at any gross weight, provided the maximum load of any one single jacking point is not exceeded. If the aircraft is supported entirely by the 3 main jacks and the stabilized jack point at D, the maximum jacking weight of the aircraft mustn't be exceeded. For axle jacking points E and F, they provide the means to change 2 flat tyres on the same axle up to the maximum of gross taxi weight. And the landing gear jacking points are integral 3/4 inch spherical radius pads under the main and nose gear axle. So they're kind of built into the gear itself at the bottom of the gear. The jacking points on the wing and body include special provisions for the attachment of bolt-on type jack adapters, where you have a standard 3/4 inch spherical radius pads. To minimize the vertical lift during jacking operation, what you can do is gag the nose and gear shock struts. So you put nose and gear shock strut retainers, which lock the oleos in the depressurized or compressed condition, and then you can lift the aircraft, and that minimizes how much you have to lift it up to clear the ground. Obviously, you can only do that if you don't need to swing the gear. The aircraft, in the right-hand main wheel well, you'll see a leveling bracket and kind of scale. So basically, you hang a plumb bob down and you'll see the leveling scale down beneath where the right-hand keel beam is. And basically, you just manipulate the jacks until you get the plumb bob in the correct position. For towing the aircraft, then you just hook up and go, but there is a maximum angle you're allowed to deflect to tow the gear or nose wheels, deflect them, and that is indicated by a couple of red stripes on the nose gear doors, which works out at a maximum tow bar movement of 78 degrees either side. Obviously, when you're towing, you need to make sure the wingtips are clear, etc., etc. You shouldn't use braking during turns except in an emergency. And before you start to turn the nose wheel, the aircraft should be rolling forward. It just avoids putting undue stress on the nose wheels, tyres and the nose leg. When you've stopped towing, the aircraft should be towed for a couple of meters in a straight line just to relieve any stresses. We're going to skip forward quite a few pages in the notes now. I just wanted to talk about the overwing exit flight lock. So we've got a couple of overwing exits over the wings, one each side or possibly 2 each side. As I said in the previous video, when we're doing the introduction, these are different from the classic series in that they are hinged upwards and outwards with a kind of gas strut and counterbalance mechanism to assist you in opening it. So it's not a true plug type door. Therefore, as a bit of a safety feature, there's what we call a flight lock installed that prevents the door from being opened if the aircraft's in flight. Excuse me. It is a fail-safe design. So when the flight lock is energized and there's a flight lock solenoid that basically stops the mechanism from working when it's energized, it is locked. That means, therefore, if there is a loss of aircraft electrical power, it means that the doors can still be opened. But basically, the flight lock mechanism prevents operation of the emergency door in flight. There's more to the logic than that, actually. There's a little bit more to it than that. It's not just a weight on wheels input. And we'll look at the logic in the next couple of slides. So the flight lock mechanism on the forward upper half of the door, just behind the hinge arm. The flight lock mechanism automatically activates during takeoff. This prevents operation of the door handle in low differential pressure and in unpressurized flight. On the takeoff, 28-volt DC goes to the door flight lock solenoid, and it gets energized, and that retracts its plunger. The flight lock solenoid plunger is connected to the flight lock pull shaft, and when the pull shaft turns, it engages in the pull with the locking torque tube. The lock torque tube cannot move out of to the unlock position until it's unlocked. On landing, the flight deck solenoid is de-energized. This permits a tension spring to unlock the flight lock mechanism, allowing the door to be opened. The tension spring gives a fail-safe function, ensures that the flight lock pull goes to the unlock position if electrical power is not available. This is the electrical schematic then for the flight lock control. So we can just walk through this. So what we have in the system, the various components are: we have a power supply, which is coming from 28-volt DC bus 1. We've got a flight lock relay, R742. We've got the actual flight lock solenoid, and there's a couple of other relays there in junction box 24, which are to do with the engine running, which are engine running relays, energized when the engines are running. And the PSEU. The PSEU is a proximity switch electronic unit. It processes all the landing gear positions, sensors, etc., etc. We're going to go through that when we do landing gear in Module 3 in greater detail. But let's have a look at the logic then for the flight lock. So we know then if the flight lock solenoid is energized, that means the door is locked and we can't open it. So let's see how we can get that flight lock solenoid to energized. So looking at the left-hand side of the picture where we have our power supply, we've got a power supply on the P6 circuit breaker panel with the circuit breaker identified as Overwing flight lock left. Okay, there's obviously a similar one for the right-hand side. And that power supply is routed to the flight lock relay, R742. Now what we need for the relay to energize, we've got power, we now need a ground signal. The ground signal is going to be provided by the PSEU. So let's look inside the PSEU, and we can see there's some logic taking place that the PSEU is processing. So what it's looking for is looking at the status of the main entry doors. So the service doors, forward and aft service doors on the right hand side and the forward and aft entry doors on the left hand side, it's looking at the status of those. If 3 out of 4 of those locks or those doors are closed, then a logic 1 will be released from the out to that AND gate at the inside the PSEU, and we have a 1 sat at that AND gate, and it's an AND gate, so we need another 1 at the bottom of it to make it work. If we get a 1 out of the AND gate, it's going to energize that internal kind of logic relay inside the PSEU. So we've got a 1 there if 3 out of the 4 service doors or entry doors are locked. So we've got a 1 sat at that top of that AND gate. Let's have a look at how we can get a 1 at the bottom. So we've got an air or ground signal that comes in at the top. So if we're in flight, that will provide a 1 out to that OR gate. And if we've got a 1 at an OR gate, it comes along straight through to the AND gate. So we would now have 2 1s sat at that AND gate. That will energize the internal logic relay and provide a ground signal. The other way we can get a 1 out of that OR gate is if both thrust levers are more than 55 degrees. So during a takeoff run, for example. So during a takeoff run, we're still on the ground, so you wouldn't have a 1 at the top of that OR gate, but you will have a 1 at the bottom of the OR gate during takeoff because the power levers are set to a high power setting. Therefore, you get a 1 out of the OR gate. So you've got two ones at the AND gate. That means you get a 1 out of it, which is going to energize that logic relay. When that logic relay energizes, you can see there's a ground signal provided, and that completes the circuit for the flight lock relay, R742. Boom, and it energizes. When it energizes, power is routed through the contacts of the relay itself and provided to the flight lock solenoid. But it's still not quite, the logic is still not quite accomplished. We've got power to the flight lock solenoid. We need a ground signal for it to work. And the ground signal will be provided if either of the two engines are running. So either one or both engines are running, boom, boom, boom. We have a ground signal provided by one of those two relays. That means the flight lock solenoid has now got the circuit completed. It's got a power supply coming in at the top because the flight lock relay has been energized by the PSEU. And we got the power supply coming through, which then routes the power supply to the flight lock solenoid, and the ground for the flight lock solenoid is provided by the fact that both or either of the engines are running. Once that is energized, the flight lock is engaged and we can't open the overwing exit. And at the top of the picture, just above it, it's got a position switch. That just goes to the PSEU, so the PSEU can monitor and know whether or not the flight lock's engaged.